Yay!
Okay, here's a slightly different kind of problem dealing with thermal energies, and this one involves a phase change of ice to water and how much energy you need to dump in order to make that happen. Okay, so kind of a typical example, maybe you have something like this. Let's say you're on a camping trip, backpacking trip, and well, I guess for whatever reason you have 10 kilograms of ice. It seems excessive to be walking around with all that, but anyway, for the sake of the problem, here's what you got. 10 kilograms of ice, bag of ice. And you also happen to have a 500-watt heater. What you really want is water for coffee. And it turns out, I looked it up, optimal temperature for brewing coffee is something like 90 degrees Celsius. So what you want to do with your heater is you want to turn that ice into water. So you can't do it instantly. It's a 500-watt heater. That means 500 joules per second is the most you can pump into this. How long do you have to wait? How long until coffee time? When do you need to get started? All right. So, I mean, really what we're saying is that we need to develop an energy budget. How much energy are we going to need to make this happen? And then if we know how much energy we're going to need, then there's just one more step to figure out the time. All right. I have 10 kilograms of ice. Here's the way it works. Oh, by the way, let's say the ice is at minus 10 degrees Celsius. That's the initial temperature of the ice. All right, we need to know that. Okay, here's how you work these kind of problems. I mean, clearly, we're going to have to go through a phase change. Ice has to turn into water, right? But not directly. So what happens is, first you need to bring the ice. Here, I'll write it down in words first. First, you need to bring the ice from 0. Oops. That starts out at minus 10, right? So the ice has to go from minus 10 to 0. And then what happens is that the ice changes phase. While it's changing phase, all you're doing is breaking those bonds that's sort of sticking the water molecules together to form ice. So what happens is you keep dumping energy into the ice. Even though it's at 0 degrees, you keep dumping energy in, and it doesn't change temperature. All that happens is you're breaking the bonds. So you need to dump a bunch of energy in to make it all water at 0 degrees. So it doesn't actually change temperature until it's all converted over to water. So that's going to require a certain amount of energy. It's called the phase change. So then you need to, what I'm saying is you need to melt the ice. And then you need to bring the water from 0, because it starts off at 0 after it all melts. And you need to bring the water up to 90. So it's a 3-step problem. Sometimes you might see a problem where then you have to turn it into steam or whatever. Well, that's cool. Then you bring the water up to 100, and then you have to go through another phase change, and then change it all over to steam, and then continue. Okay, so how do we do it? Take the first step. How much energy is it going to take? All these steps require energy, right? So how much energy it take to go from ice at minus 10 to 0? Well, that's just going to be the mass. Let's suppose we don't lose any mass, right? It's all the same mass all the way through. So this is just going to be the mass times, well, for every degree and every kilogram of ice, how much energy does it take? Well, that's the specific heat of ice. We would just look it up or something. And then this would be the delta T, right, for the ice. Okay, so that's that first step. The second step, let's skip it just for a second, and then we'll fill it in. Water, we already know how to do that. How do I take water from 0 to 90? It's that mass times the specific heat of water times delta T water, 0 to 90. So it'd be just 90. Okay, melting the ice. It's not quite the same equation because there's no change in temperature. It stays at 0, but we go through a phase change. So it's actually easier. All we have to do is look up, oops, it's the same mass times this thing called the latent heat. Again, don't worry about the vocabulary. The units of it tells you all you need to know. It's just, I mean, if you look, the units have to be, you need to get joules out of that, right? So it's got to be joules per kilogram. So it's just something you look up for every material. How much energy do you need to pump into this thing to melt it? It's just a number, and so we can look it up. So there you go. That's it. Those are the three pieces. So let's compute it and add all these things together. So the mass is going to be over here. I got 10 times specific heat of ice. I looked that up. It's less than water. It's like 2100 times 10, the temperature difference. Then I got to melt it. And when I melt it, I have my 10 times my mass. The latent heat, for every kilogram of ice that you want to melt, you need to put in, it's a big number, 333,000 joules. There we go. Then I got to add in my last thing. Still the mass, 10 times specific heat of water is like 4,200 times our temperature difference of 90. I mean, I could factor out that M, right, to make it just a little bit easier. But I think it's important to keep all this stuff separate right here, just so you can see where all the little pieces are coming from. So it's a three-step process. There's three different sort of places where you need to put energy in to get something to happen. So when you compute all of these together, what did I get? I got like 7.32 times 10 to the 6th joules. Okay, that's our energy budget. That's how much energy we need in order to get the ice up to hot water for making coffee. The problem is our heater is only a 500 watt heater. So if we divide by 500 watts is 500 joules per second, right? That's how we get time. So if you divide these things out, I get, what did I get? 14,640 seconds. That's a lot of seconds. It's like 4 hours. All right, so even if all the heat from the heater goes into melting the ice, which is probably not terribly realistic, you're still going to have to wait at least 4 hours before it's coffee time. So yeah, again, this technique of dividing by the rate at which you put energy into something can give you the time. That's something that's used pretty often in problem solving. And then the other thing that we did was changing phases. And the whole idea with changing phases is that term. Because the temperature difference is 0, we look up a different constant called the latent heat. And all that refers to is just breaking the bonds in order to melt something. If you were turning the water into steam, or if you were vaporizing something, it's called the latent heat of vaporization, but it's the same term. So for water, if you wanted to turn all that into steam, you would do the mass times the latent heat of vaporization. And this, for water, this is a really big number. I don't remember what it is exactly. It's like 2.3 times 10 to the 6 joules per kilogram. It's an enormous number of joules per kilogram. I guess that sort of makes sense, because if you put a pot of water on the stove, maybe it'll take 10 minutes to bring the water up from room temperature to boiling, right? But how long would it take if you just sit there and watch it for all the water to boil away? Well, that's going to take a really long time. So it does require a whole bunch of energy to completely vaporize something. But what's interesting is that turned around the other way, that process releases a lot of heat. So when steam condenses, right, the opposite of evaporation or vaporization, the opposite of that is condensation. So when steam turns back into liquid, it releases 2 million joules per kilogram, which is a lot. So you might see problems dealing with how awful steam burns are, because when they condense if there's steam on your skin and it condenses, it creates an awful lot of heat. Condensation of the atmosphere is part of the energy that drives hurricanes. And so, yeah, it's a lot of energy. So this is used all over both physics and meteorology.